Hello viewers and welcome to another lesson on calculus. Today we are looking at the application of differentiation under which we are considering the rates of change. Um, Before we delve into solving problems, let's look at this important note. Let's say we have y to be a function of s, okay? Then the change of, the y dx can sometimes be regarded as the rate at which y changes with respect to x. Remember, in this context, we take x as the independent variable upon which the variable y depends. Now, there are two things to note. When the change in y with respect to x is bigger than 0, we say that y is increasing as x decreases. On the other hand, if we have the y changing y with respect to x to be less than 0, then we say that y decreases as the x value uh, increases. Now, it is worthy of note that when you are solving problem regarding rate of change, it is important to remember the chain rule or function of function principle. It is pivotal in solving problems under this heading. Now, here is a question before us. We are told that a circle with radius 5 centimeter, increasing at the rate of 0.2 centimeter per second. The question is, what will be the corresponding increase in the area? The corresponding increase in the area, what they mean by that is, how is the area of this circle increasing with respect to what? With respect to time. Now, just think about solution. Think about a circle of this nature. You have a circle here. Let's say this is a circle, and from here to here gives you the r. But why this is 5 centimeter, we know that this radius is changing, maybe because of a rotation going on. And so we can have, since it's increasing 0.2 centimeter per second, then maybe after 1 second we will have something of this nature, such that this extends to this place, and if we can call this our r prime. So this is increasing, the increase is 0.2, is increasing by 0.2, and then it continues like that, and then you are extending the rate. This will go like this will be r prime prime, and so that is how the increase is happening as the time goes by. So that is the situation we are dealing with here. It's like a ripple effect, just spreading outward. Now, if that is the case, what formula or equation are we using here? From the question given to us, we are dealing with a circle. The area of a circle, equals pi r square, okay? And they said the the initial radius is going to be 5 centimeter. That is when the increase has not started, or maybe before the rotation, before the gyration, whatever action might be taking place leading to the increase in the radius. It hasn't happened yet. The radius was 5 centimeter, and the rate at which the change was happening, so that will be our dr over dt. Radius is changing with respect to time. That is 0.2 centimeter per second. All right. Now the question says, what will be the corresponding increase in the area? Like I mentioned to you, we are using the concept of chain rule in this regard. So we have dA over dt. That's what we want to look at. Will be dA over dr times dr over dt. So the area of this particular circle is actually changing with respect to what? The radius. And then whatever you get, you multiply it by the amount in which the radius is also changing. And that forms a chain rule right there. And so we can proceed here. dA over dt. What is dA over dr? You are looking at this and you are differentiating it with respect to r. This, if you differentiate this will be, you remember this, your pi is a constant, 22 over 7. If it is given that way, that will be 2 pi r. We have differentiated this one. This is our 2 pi r. Now multiply, remember this dot product, you can just keep it like this. Our dr over dt is already given to us, and that is 0.2 centimeter per second. You can ignore the unit, and when you are done, you bring it back. Now, look at this. We have our radius here. That will be 2 pi times 5 times 0.2 centimeter per second. This is 10 pi times 0.2 centimeter per second. 10 times 0.2 is just 2. So this is 2 pi centimeter per second. So that will be our answer. Yes, this is yet another question on the rate of change. Remember, calculus is what we're dealing with. The question reads us, if the volume of a hemisphere is increasing at a steady rate of 18 pi meter cube per second, at what rate is its radius changing when it is 6 meter? Now remember that the area of an area of hemisphere equals to 2 over 3 pi r cube. That is half the area of a sphere. And then what are we given? We know that they said if the volume is increasing at a steady rate, the rate of change of the volume, that's the dV over dt, is 18 pi. Let's ignore the unit for now. And we are given the radius. Radius equals to 6 meters. The radius is given as 6 meters. Now to write the chain rule for this derivative, we have this dV, change in v with respect to the radius, and then multiply by the little change of the radius with respect to time. This is what we are going to have. And here we are asked to calculate this part. At what rate is its radius changing? That is what we are particular about. So we know this one already, and then we can get this one also. Here our dV over dr, you just look at this particular formula and then differentiate it. If you bring this 3 to the front, that will be 3 multiplied by 2 over 3 pi r square. We have differentiated that, and this 3 will cancel this 3, and so we have 2 pi r square. Don't forget, this is just a dot product, and we can now write this as dv over dt equals, this becomes 2 pi r squared, and then multiplied, I can change that for better understanding, I can change this to times. The r over dt, we don't know, although we know this one to be 18 pi. So 18 pi equals to 2 pi r times the r over dt. Obviously, you know that this pi will go with this pi, and 2 here is 1, 2 here will be 9. And so your dr over dt will be equals to 9 divided by r squared. And what is our r? This is 9 over 6 squared, and that will be 9 over 36, and that will be 1 over 4. Okay, and what is 1 over 4? Our our dr over dt equals to 1 over 4, and in decimal that will be 0.25 meter per second. And that will be, and C is going to be our answer. I hope you understand. Hello viewers, and welcome to yet another aspect under application of differentiation. In this lesson, I'm not solving any problem, but then I want to give you a clear distinction between partial derivatives and implicit functions. You will get to know when you are dealing with partial derivative and when you are dealing with implicit function. Number one, partial derivatives is used when two or more independent variables, e.g., r and h, are involved. If you have two independent variables which are expressed explicitly with a dependent variable as its subject, we say it is a partial derivative. On the other hand, it is an implicit function when the equation cannot be explicitly solved for one variable, just as you have this. This is the equation of a circle right here. We cannot explicitly solve it because of these terms that are given here. Now, another thing to take note of is that the independent variables have no relationship with each other. Over here, it's a partial derivative because the independent variables have no relationship with each other. For example, change in r does not affect change in y. All right, they are mutually exclusive, they have no relationship. On the other hand, variables depend on each other for implicit function. Y is a hidden function of x. As you can see here, y is a hidden function of x. So we only differentiate through by what? By x. That is what we do for implicit function. But in this case, because this r and h are mutually exclusive, they have no relationship, we differentiate them individually. We differentiate the entire function with respect to r, then with respect to h. Another thing is that the notation, for the notation, a curly delta symbol, you can see that, is used. E.g., for the volume of a cylinder, then the partial derivative del v del r, that is partial derivative of v with respect to that of r, is 2 pi rh. In this case, h is kept constant. But over here, we are dealing with the derivative, the differentiation of v with respect to h. Hence, we are keeping r constant. We only differentiate it, and you can see that h is no more there because it's a result of the derivative. But under implicit function, we keep it as dy dx. All right. On the board is another question under rate of change in in the application of differentiation. And the question reads us, the radius of a cylinder increases at the rate of 0.2 centimeter per second, while the height decreases at the rate of 0.5 centimeter per second. Find the rate at which the volume is changing at the instant when r, the radius, is 8 centimeter and the height of the cylinder is 12 centimeter. Now, this is the cylinder I've drawn on the board. What you don't want to do is to label it 8 centimeter and the height 12 centimeter. That's because this is not the final height. Neither is this the final radius. Hence, it is appropriate to just keep it as r and what h. They are changing. Now, the first thing is that what is the volume of a cylinder? Volume of cylinder equals to pi r square h. That's the volume of a cylinder. And if you look at the formula for that, you will discover that the volume of a cylinder has two independent variables. That is the radius and that is the height. And so we want to write a formula for that, a chain rule for that. And so this will be our change in V, our dV over dt. What will it be? It will be, look at this. Let's assume that we don't have our h there. We don't have h here. Let's take, for instance, how would you write it? The chain rule will be dv over dt, dv over dr, that's with respect to radius, then multiplied by dr over dt. Isn't that the way you are going to write it? Of course, yes. But then there is h, which means that what you are going to use now, remember the principle for applying partial derivative is that you have two or more independent variables. And here we have two independent variables. Hence, this is going to change to the v over the r. But this is going to stay like that because this r is an independent variable. So it's changing with respect to time. Okay, so it is going to stay like this as the usual derivative coefficient dr dt. Now, plus, remember, if we are saying these are two independent variables, then we are going to also use the product rule. In this case, what have we done? We've kept the h constant and we've differentiated the function v with respect to what? R. But now we are going to keep the variable r constant and then differentiate the entire thing with respect to h. So this will be the v over the h, the h over, dot dh dt. Remember, this is the amount at which the height is increasing with respect to time. So this is what you are going to have. For that, what will be, we already have the r dt. The r dt is given to us as 0.2 centimeter. Ignore the other one. Okay, let's leave it like that. The r dt is 0.2 centimeter per second. Now let's look at the v over the r. The v the r, look at it, that will be equals to 2 pi rh. It means differentiate only the radius, which is squared, and that these two will come forward, and then you have 2 pi rh. Now, what's the next one? The v over the h. Our the v over the h is that you keep your radius constant, don't touch the r, and then differentiate the rest. If you differentiate h here, you'll get 1. So this is going to be pi r squared. And then what is the next? Oh, we are also given the h change. You can see the I decreases. When you hear the word decrease, that's negative right here. So that will be negative 0.5 centimeter per second. That is what we are given. Now let's plug the entire thing into this particular equation. So our the V over the T equals to what? Our the V over the R gave us 2 pi RH, 2 pi RH times our dr over dt is 0.2, this in bracket, plus the v over dh. The v over dh is pi r squared times negative 0.5. Okay, that is what we are going to have. Next thing is that you check, can you factorize? That is the easiest way to go without confusion. Pi r is here, pi r is here, factor it out. This will be pi r factored out. What will be left here? That will be 2h times 0.2. Because of this minus, everything will minus, negative, minus 0.5 r. That's what you are going to get. And then you have pi. Our radius is 8. Do not forget, we are given the radius to be 8 centimeter. So this is 8 pi. And our h is 12. 2 times 12 is what? 2 times 12 is 24. Okay? So we have 24 times 0.2. And then minus 0.5 times r. 0.5 times r, that will be 0.5 times 8. Okay? And then our 8 pi, we have 8 pi. 24 times 0.2 would give us what? That will be 4.8. And 0.5 times 8 is what? That will be 4. And this will be equals to 8 pi times 0.8. Okay? And so what is 8 times 0.8? What would that be? 8 times 0.8, that would be, let me clean this right up here. That would be 6.4 pi centimeter cube per second. That is what you are going to have. And if we plug in the value of pi, perhaps 3.142, we will get a value. Okay, but in terms of pi, that is what you are going to get, and that will be the end of this lesson. Don't forget to follow for more.